Welcome back to Physics Made Easy, Part 7. Well, this week's learning objective is to look at magnetic fields, and you may know from prior learning that anything that carries an electric current has a magnetic field associated with it. Let us just take a straight wire, and now I'll have to draw this in such a way that this actually represents the current coming out of the board. Okay, so if you imagine a wire and the current is coming out of the board. If you take your right hand, and place your right hand around the pen, and the thumb indicates the direction of the current, and if you notice the direction in which the fingers curl gives you the direction of the field. Now they will get further apart, because the further apart they are, shows you that the field is actually getting weaker. So there we go. Just to represent that once more, thumb, direction of current, fingers, direction of field, the direction in which my fingers are curled. Now what we said was that a current carrying conductor placed in a magnetic field experiences a force. So I'm going to take this conductor here and place it in this field, represented externally, of course, in a different colour. So let us just place this wire in this field. Now, there's the wire. Let us just draw the field lines in. We'll draw a few in. And you will notice that on one side of the wire, the orange and the black arrows oppose each other, and in the other side, they're in the same direction. In other words, the field, if you like, weakens on this side, but strengthens on this side. If the field is stronger on this side compared to this side, this wire will then move upwards. We'll come to working out how to work out the direction of motion in a moment. Let us just demonstrate this practically, so you can actually have a visual, just to prove to you that a current carrying conductor will experience a force. We will now demonstrate to you with a DC power supply set at 2 volts, and we will identify for you the red terminal, which is the positive, and the black as the negative, and we will pass a direct current through these conducting wires. My assistant will place a rider to make electrical contact. A magnetic field will be brought in position. We will switch on the current, and you can see what happens. It experiences a force. What we will do now is reverse the magnetic field, and you may want to predict what happens on this occasion. And my assistant will demonstrate this again, and as you see, it actually moves in the opposite direction when the field is reversed. So now, coming back to the board, if you take your left hand, and mutually hold the first finger, second finger mutually at right angles, the first finger represents the field, the second finger represents the current, and my thumb is pointing upwards, which is in line with the arrow. Now, let me give you a better representation of this. So, here we go. Here is a much magnified image of a hand. The thumb indicates the direction of the motion. Motion. The first finger represents the field. The second finger represents the direction of the current. I've labelled the thumb with a capital here to indicate the motion. That's a capital to indicate the field, and the letter C, made it slightly larger so you can remember it represents the current. This rule is called Fleming's left-hand rule. A couple of minor points here. The current always flows from the positive to the negative, and you have noticed on the demonstration that we identified the positive terminal for you and the negative, so this flows from positive to the negative, and the field always runs from the north to the south pole of the magnet. Thank you for watching.